Hi guys, today I will be talking about the fast explanation method on matrix. Fast explanation is a tool that for people to calculate the power of a number in a fast way, and it comes from the idea of divide and conquer. And it can also apply on the matrix, but it's not an application. It's such a nice tool to use to solve applications that can be modeled into the power of matrix. And you will see two examples later. Let's see the first example so that you will know the brief concept of what it is. Let's say we want to calculate the 7 to the 10th power. And the naive solution will be just multiplying 7 by 9 times. And the fast explanation algorithm will do the following things. First, it's converting the 10th, the power, to a binary number, which is 1010. And now let's recall what we learned from algebra. Let's say a to the power of b times a to the power of c will equals to the a to the power of b plus c. So the 10 can be divided into two numbers, which is 2 plus 8, because the binary number is this one represents for 2, which is 2 to the power of 1, and this one represents the 2 to the power of 3, right? And each power is 2 times, or 2 times 2, which is 4 times or 8 times bigger than the previous one. Okay, therefore 10 to the 7 can be represented as 10 to the second times 10 to the 8th. In this case, we only need to calculate 7 to the first power, 7 to the second, 7 to the fourth, 7 to the 8th, and we pick two of them, which is 7 to the second and 7 to the 8th. We pick two of them and multiply them together. So totally we need to calculate this 4 numbers, so 4 times, and the last multiplication, which is 5 times. So it's 4 times less than the naive solution of the calculations. You may think that, wow, the simplification does not seem obvious because it's like 9 and 5. Let's take another example. Let's say we want to calculate 7 to the 1000th power. The naive solution will calculate 1000 times, maybe 999 times to be accurate. But for the fast explanation method, it only needs to take, let's say, 7 to the 8th, 7 to the 32, 7 to blah blah, because we can convert the 10, actually we can convert the 1000 to the binary number, which is this one, and it has 10 bits. So we only need to calculate, because we don't count the 7 to the 0, because that's just 1. And we don't count, but we do count the 7 to the 11th bit. So totally we will, I mean 2 to the 11th. So totally we will calculate 10 different numbers, and we pick 1, 2, 3, 4, 5, 6. We pick 6 of them, and we multiply them together. So the total multiple time will be 16. Actually, maybe 15, but one time doesn't matter. So, and we can now you will see the huge difference. It's speeding up from 1000 times of calculation to 16 or 15 times of calculations, and we can easily tell that if you have studied how to analyze the time complexity of an algorithm, if you are a computer science major or you have learned such classes from, let's say, discrete math, you will see that the calculation times for the fast explanation algorithm is positively related to the number of the bits that the binary number of the power is. Let's say 1000 here is 10 bits, and the 7 before, the 10 before is 4 bits. The time complexity will be O, the big O of log 2n. If you have not learned what big notation is, don't worry. You can simply image that if you need to take 1000 seconds to do something after implementing such algorithm, the time will become about like 10 seconds, 15 seconds. So that's what's the difference. And here is the code on how to implement the linear, because all I talked about is just a linear explanation. So here's the code about how to implement the linear fast explanation in C++. without considering the overflowing, because it's an integer, so it may be overflow. Due to the lack of time, I am not going to explain the codes in this presentation today, but it's very easy to understand, and it's just doing what I just said, like converting the power, which is n here, to a binary number, and take care of each bit, which is n1. We take care of each bit, and we shift n to take care of each bit. Okay, and now let's talk about the matrix multiplication and exponentiations. If we want to multiply two matrices A and B, we simplify multiply A's each row. Here is A's each row and B's each columns of each element. So we multiply them together and add them all together to be one element of the outputs element. And it's very easy to understand, and since you have already known, you must already know how to do it because we are taking the linear algebra class. And since we want to do explanations on the matrix, then such matrix must be the square matrix, and that's obvious, right? And just like a number of power, like the linear power that can be divided into small pieces, the power of a matrix can also be divided into a binary number. So the power of a matrix can be divided into pieces also. Here's an example here. If we have, for example, if we have a to the 1,000 power, a is a matrix, then 1,000 can be divided into a binary number as we did before, and we can just calculate a to the 8th power times a to the 32 power times a to the 64 power, and blah 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 until a to the 512 power. So it's the same thing, and we have speed up the calculation from on to log 2n times the t, and which t is the I think I forgot the big O notation here, but and the t is related to the size of a matrix, because the matrix can have n rows and n columns, so that's related to the size of the matrix. But it's a constant, so we can omit that. But I just put it here for be more accurate. And let's talk about the most excited part that I think it is the application on matrix explanation, which is the linear sequence. Let's since I've already introduced what fast explanation is, let's see the example. Find the nth element of Fibonacci sequence. I think most of you have already heard of or already like play with Fibonacci sequence already. It's defined as 1, 1, 2, 3, 5, 8, and infinity. It's the number of each element is the sum of previous two elements. So 2 is the sum of 1, 1, and 3 is the sum of 1 and 2, 5 is the sum of 2 and 3, and the formula is like this. And if we want to find the nth element of Fibonacci sequence, we can do it in iterative way or recursive way, which is counted as linear method. However, if n is such a big number, let's say 10 to the 18th, then even a fast modern computer will take forever to compute by using the linear method. But we can solve this question in an efficient way by using the matrix explanation algorithm. Okay, let's define a matrix A to be 0, 1, 1, 1, and we can tell from what we learned from the class. A is the elementary matrix, and A times B will do the transformation as following. We take the second row of B to be the first row, and we add row 1 and row 2 to be the second row. As we can see, 0 times the first row and 1 times the second row to be the first row, so which we just take the second row to be the first row of B. And then we take the we add row 1 and row 2 together and put it as the row 2. So here is how we implement the multiplication. A times, if we have a vector fn and fn plus 1, we would have fn plus 1 to be the first row and fn plus 1 to be the second row. And we know from the formula here, fn plus 1 will be fn plus 2. So if we do it in the backwards, we will see such implementation. fn plus 1 equals to a times, we subtract 1 of each sub number, which is the n and n plus 1 here. So, and we can keep subtracting by just adding an a before it. So we would have fn minus 1, the vector would equals to a to the power of n minus 1 times the vector of 1, 1, which is f1 and f2, and that's defined as the base here. f1 and f2 are both 1. So we can how do I say that? We can simplify fn plus 1 into a to the power of n minus 1 and times the vector of 1, 1, right? So now what can you see? The question of finding the nth element of Fibonacci sequence becomes a question of how do you find the n minus 1 power of a matrix A. If we find the a to the n minus 1 power, we can and multiply the vector of 1, 1, we can have fn and fn plus 1, and we take the first row, that's the nth element of the Fibonacci sequence. And since it's a matrix power in a to the n minus 1 power, we can then apply the fast exponentiation method on the matrix to divide to simplify the ON, the iterative or recursive linear method, to a log n method, right? And the next few paragraphs will discuss about the complexity analysis and consider the fellows that haven't taken such classes or not in computer science major. I will skip it. Let's check another example, which is a little more complicated than the Fibonacci sequence one, but it's still, we can apply the same method. Okay, so let's say we have a sequence an equals to this, and we can define. I don't know if I have enough time. I would just put it here, and I would just try to explain this example and finish it, the presentation. So let's define an equals to 1 if n is smaller or equals to 2, and an equals to, let's say, 2, this formula. And we can define such a matrix that to do the operation to let each sub number adding 1, like what we just did for Fibonacci sequence. And now we also do backwards, so the an can be represented to a to the nth power times 1, 1, 1, which is the base vector of the sequence. And now the question also becomes a matrix power, which we can implement the power of the matrix fast exponentiation method and times a vector to speed up the calculation. And finally, but I don't have enough time, is Markov chains. We can also apply the matrix fast explanation Markov chains. You can find Markov chains in the book on, I think it's section 6.3. It's discussing about what Markov chains is and how it implements to the matrix power, but it didn't talk about the fast explanation method. So, but we can apply it to that. We can also do it in a diagnosing matrix, but applying matrix fast explanation algorithm won't be that bad because it's so easy to program. And also, you can pause here is the code of how to implement the fast explanation method on the matrix. And that's pretty much about the presentation. Thank you.